में रहता है रिकॉर्ड पे और देखने को अनुपम दिखता है।
दिखता है, कभी निकालता है।
हाँ
कभी निकालने के लिए देखता है।
वो पीछे का मतलब है।
वो पीछे पड़े माइक की न्यूज़ स्टूडेंट में क्या है तो निकल गया।
ये हमारे स्टूडेंट है आइजर में है ना अभी इज इट आइजर
So we'll be starting with receiving with the competition.
अच्छा आप नहीं पढ़ा मेरा पहला है
So, I'm Ayush and I will be talking about visualizing the Earth's nodes. This was a project in seismology that I worked on under the guidance of Professor Arjun Datta, who, like Professor Hitanjali pointed out, was a St. alumni. And he's currently working at So this will be the structure of the talk. I will give a little bit of theoretical background. Then I will talk about the mathematical machinery required to represent the Earth's oscillation. And then I'll finally show some animations that I created, like the one on the right. So I'll start by talking about normal modes, which I'm sure we're all familiar with. These are oscillations of the system where the entire system moves at the same frequency, producing what we call standing waves. You can see the first four normal modes of a string that is fixed on both ends of the curve. And the property of normal modes that we are interested in is their orthogonality, which means that you cannot create or recreate any one of the normal modes by combining any of the other modes. This is similar to the orthogonality of basis vectors in linear algebra, and it is the reason we can represent any arbitrary oscillation of the body as a combination of its normal modes. Here is a visual example of this. So here we have an arbitrary oscillation which looks pretty complicated, but we can actually recreate that by simply adding four normal modes of the string with different frequencies and different wavelengths. So the Earth is also a rigid body which can oscillate in different ways, and therefore we would like to be able to represent the seismic oscillations such as those produced by earthquakes in terms of the Earth's normal modes, because those are much easier to study and to work with mathematics. So since the Earth is a little more complicated than a string, it can oscillate or it can undergo two different kinds of motion. It can undergo compression, which can be thought of as the expansion or squeezing of a rubber ball, and torsion, which can be thought of as twisting of the surface of the entire ball. So there are two different normal modes for the Earth. Spheroidal modes correspond to compression and toroidal modes correspond to torsion. So there is radial as well as transverse motion in spheroidal modes, whereas there is only transverse motion in the toroidal modes. And because of that, there is a volume change in spheroidal mode, but no volume change in the toroidal modes. So next I'll talk about the math required to represent these normal modes. And I'll begin by talking about spherical harmonics, which are denoted by the symbol y with the superscript of m and the subscript of l. These are the two orders. The m order is called the azimuthal order and l is the angular order. I'll explain what those mean in a moment. But spherical harmonics can be thought of as being analogous to trigonometric functions in Cartesian coordinates, and they're essentially used for describing different patterns on the surface of the sphere. So they're functions of theta and phi, and they return a scalar, which is usually complex. So the azimuthal order denotes the number of nodal lines that pass through the poles, and the angular order denotes the number of nodal lines in total. This will be more obvious with these plots. So what I've done here is computed the real parts of spherical harmonics of different orders and plotted them. Red represents positive values, blue are negative values, and white are values very close to or equal to 0. So you can see that when L equals 2, we have two nodal lines, neither of which pass through the poles. When L equals 3, we have three nodal lines, all three of which pass through the poles. And over here we have four nodal lines, two of which pass through the poles and the other two don't. So this is what the spherical harmonics give us, which is essentially different surface patterns. Now that we know about spherical harmonics, we can start actually defining the normal modes of the Earth. And we know that these should be functions of r, theta and phi, because there should be some angular dependence as well as some radial dependence. And they should give us a displacement vector for each point in the Earth as the element. So the angular and azimuthal dependence in the normal modes comes from from what are called surface vectors, and the radial dependence comes from what are called eigenfunctions. So this is just representative of the displacement caused by the different modes. So these are toroidal modes, and you can see that there is a radial dependence coming from the eigenfunction. This is this surface vector which gives us the angular dependence, and then there is the standard e to the I over t term which gives us the time dependence. Similarly, for the spheroidal modes, we have two eigenfunctions and two surface vectors, and I'll explain why there are two in the next slide. So these are the toroidal modes which are simpler. And what I've shown here are the r, theta and phi components, that is the radial, polar and azimuthal component of the displacement. So since toroidal modes involve no radial motion, that is motion in the radial direction, the radial component is 0, whereas the polar and azimuthal components are non-zero. And both of them are represented in terms of the spherical harmonics that we looked at earlier. And for the spheroidal modes, we have two surface vectors, one of which gives us the radial component, and the other one has no radial component but gives us the angular component. And the reason there are two of them is because there are two eigenfunctions which are multiplied with the surface vector. So we cannot combine these two surface vectors since they have different corresponding eigenfunctions. So with the surface vectors alone, we can start creating animations for the surface of the Earth alone. We haven't looked yet at the radial dependence. We've only looked at the angular dependence. So we can only create animations for the surface, which I originally created using the matplotlib package in Python, but after running into a lot of limitations, I switched over to another package called Mayavi, which is more suited to 3D animations. So these are some animations that I created. So this is what is called the rugby or football mode of the Earth, where the Earth sort of inflates and deflates into a rugby shape. And these are some other orders. This has L equals 3, and you can see that it takes a conical shape. And over here the M order is 1, so the motion is a bit harder to make it red physically. And these are some toroidal modes. So over here the L order represents the different directions in which the twisting happens. So over here L equals 2, which means the two hemispheres of the Earth move in two different directions, as can be seen here. Over here L equals 3, which means that the top part, the bottom part of the Earth move in the same direction, but then the middle is moving in the opposite direction. And over here the M order is 1, which means the rotation or the twisting is happening along a different axis, as seen from the poles. All of these animations are heavily exaggerated because if they were made realistic, we wouldn't be able to see the displacements at all since they're very small. Now we'll come to the eigenfunctions, which give us the radial dependence of the displacement. So these are called eigenfunctions because they are obtained by solving the elastic wave equation for a spherically symmetric and isotropic Earth. And because they depend on the constraints given by the system itself, they are calculated for a specific model of the Earth. So I use what is called a one-dimensional Prem no-motion model. So a one-dimensional Earth model essentially assumes that there is no angular variation in the density or any other parameters that we care about. We only consider a radial dependence. So it's just a function of radius, and we get various parameters as the output based on what radius value we're looking at. And I also had to use specialized code that I did not write, which is very complicated. And this code was called Minimus, and I used that to compute these eigenfunctions shown on the right. So I'll just explain what these plots are. These are for different toroidal modes, as mentioned on the top. So the top represents the surface of the Earth, and the bottom here represents the core mantle boundary, which is the boundary between the lower mantle and the outer core, which is a liquid. So since the outer core is a liquid, it cannot undergo any kind of shear or torsion, which is why we see that the function goes back to 0 at the core mantle boundary. So the center here is 0, the right is positive, and the left is negative. And when we come to the eigenfunctions, we introduce another order into this, which is called the radial order n, which is the subscript on the left over here. So that denotes the number of times that the eigenfunction is switching signs. So over here the n order is 0, which means the eigenfunction remains positive throughout, but it is decreasing slightly. Over here the n order is 1, which means the eigenfunction switches signs once and the magnitude also changes. And then over here we have higher n orders, so the eigenfunction changes signs multiple times. And so what the eigenfunctions give us is essentially a dimensionless output, which just acts as a scalar for the displacements which we calculated earlier using the surface vectors. So I will now give a more detailed mathematical description of the displacement functions that we looked at earlier. So these are now functions of r, theta and phi. This is the eigenfunction which gives us the radial dependence. This is the surface vector which gives us the angular dependence. And then you have the time dependence coming from the harmonic term. And similarly, we have the spheroidal mode over here, which has two eigenfunctions and two surface vectors. So finally, with all of this, we can start creating 3D animations, truly three-dimensional animations, which show us the radial dependence of the displacement of the Earth. So those look like this. So what we're seeing here is a sort of cut, like half of the Earth oscillating under the T n equals 1, L equals 2 normal mode. This is similar to the one we saw earlier over here, which essentially just involves the two hemispheres rotating in opposite directions. But now we have the added complexity from the mn order, being 1, which means that as we go deeper into the Earth, the direction of oscillation changes. And so we can see that the lower mantle over here oscillates in the opposite direction as the outer hemisphere. And similarly, we have some spheroidal modes over here, and we can see that the inner layers move with a different magnitude and also in a different directions in some cases. And yeah, so these are the animations that I essentially set out to create. And yeah, so to summarize, the Earth has two different kinds of normal modes: spheroidal, which corresponds to compression, and toroidal, which corresponds to torsion or shear. The normal modes can be represented using surface vectors, which give us the angular dependence, and eigenfunctions, which give us the radial dependence. And the eigenfunctions were calculated for a particular 1D Earth model, which assumes no oceans, called Meera's. The program used to calculate the eigenfunctions was Meera's, and I created these animations using a Python package called Meera.
Can you show the toroidal motion equation?
Okay.
Yeah, this one. I'm seeing a very strong resemblance with the system that we deal with in quantum mechanics.
Yes.
Yeah, can you just for the hydrogen atom, I'm thinking about.
Yes.
That those are the same. So if I'm asking when I'll be finding the eigenfunctions of that, can I derive those eigenfunctions by just similar having a one-to-one correspondence? I mean, I already have solved this equation for hydrogen atom, and I very well know the eigenfunctions from that system.
Yeah.
Can those eigenfunctions be used here?
I don't think so, because the constraints in this case come from the structure of the Earth itself. It comes from solving the elastic wave equation, and we use a particular model for the Earth. We assume it is spherically symmetric and isotropic, and it is also a rigid, like a filled body. So I think the dynamics of this system are slightly different. But the surface vectors are similar in that they are represented in terms of the spherical harmonics, which we also see in quantum mechanics. But the eigenfunctions, I think, are more specific to the rigid body.
I mean, if I can just start with assuming those to be as my eigenfunctions, I can just run based on, I can have different parameters, you can say adjust different parameters and set and tune them up to get the results that I have for the other physical parameters that we will. So I'm just thinking of that way of approaching the solution of these kind of functions.
I mean, one difference that I can think of is over here there are no limits as such on the radial, on the value of the radius.
Yeah, for the spherical I get it, yeah. But for that toroidal part, I'm just seeing a very one-to-one resemblance.
Yeah, but what I was saying was that in quantum mechanics we have discrete values of the radius which are allowed, and not all values of the radius are allowed. Whereas in this case, we can look at the displacement at any value of the radius. So I don't think there will be a one-to-one correspondence,
But just for the case, for the nature of expression, I'm just talking.
yeah, I think, I mean, the equation is definitely very similar in that we have the angular dependence which then gets scaled by radius. So I think it would be similar, but I'm not too sure.
So you worked out with one model that you've taken for the.
Yes, so I use this model called the TEM motion model, and there are various different models which can be used by the package called Meera. But this
This is the simplest model, is it?
yes, so it assumes that there are no oceans, so the space that is occupied by the oceans is assumed to be filled up by the crust, so it has the same density as the crust, and it's also a one-dimensional model, so we assume no angular variations, only a radial variation in the density and any other parameters.
Will you actually check it with data?
No, so that was the longer sort of vision for this project, which was to take actual seismic data and to perform Fourier analysis and to then look at it in terms of the nominal frequencies. But I did not have enough time, and Professor Datta was also busy with other
So
projects.
if I just want to look at one physical situation, that one physical situation could be a superposition of, it could be a combination of, can it be a combination of both the modes?
Combination of both modes, spheroidal and
Yes.
yes.
Or you always see in, the two modes they appear as two different situations physically, or can there be a physical situation where it's a combination of both?
As far as I can remember, there are two different kinds of waves. There are surface waves and there are subsurface waves.
Yes.
So the subsurface waves are represented in terms of the spheroidal modes, and the surface waves have more to do with the toroidal.
So when we have whenever we have any kind of seismic activity, what I want to know is, whenever we have any kind of seismic activity, is it always that you either have, what I'm trying to say is,
So there will be both. So
both. It's
if
a combination of.
yeah. So if there's an earthquake, it will produce both surface waves and subsurface waves. So we will observe what is like the final displacement of the entire Earth will depend on both the spheroidal and toroidal.
So can
So
that?
combinations will-
I know you've started. It's a very maybe it's a preliminary first level work, but the software that you use, even if I work with no ocean model, can I look at a combination of? Is it possible to do simulation as a combination of a real physical situation?
So actually, Minios, what it essentially does is if we give it a particular normal mode, it gives us the eigenfunction for that mode.
Okay.
So Minios itself cannot be used for any size.
So what do you mean by give you the eigenfunction? Is that it gives you a kind of solution to your whatever situation you are giving it. I'm trying to understand.
Oh, no. So essentially, we ask it for the radial dependence of the displacements of a particular normal.
Okay.
And so, if we want to understand,
understand.
so if we want to understand seismic activity in terms of the normal mode, we'll first have to figure out which normal modes make up that oscillation,
Right.
and then go to Minios to find the eigenfunctions for those.
Right. Okay. So there is a preliminary work that you do
Yes.
before you feed it, and that preliminary work is like is where the physical situation is.
Yes.
Okay.
Since you're looking at the seismic waves and all that, how are you weighing R? I mean, what is the constraint of R? R can go from zero for anyone. In this case, of course, R is the final. So, what are you looking at?
So the constraints on R depend. I mean, we can technically calculate all the way from the center of the Earth to the surface of the Earth. Those are the ultimate constraints. But then we also have different constraints for the two different kinds of modes, because we have like one, the spheroidal modes deal with compression, Um, and the toroidal modes deal with torsion. So the different layers of the earth have different composition. And so the outer core, for example, is liquid, which means it cannot undergo any torsion. So if we're calculating for the toroidal modes, we can't. That
I'm
gives us
just
the limit.
asking what was your constraint? What is the range of R that you choose for working happen?
Oh, yeah. So I chose R to be all the way from the center of the earth to the surface. And but what we get in the outputs for the eigenfunctions clearly shows us that the toroidal modes cannot happen at all for the liquid. Yeah.
Liquid,
The liquid.
the molten part.
Yeah. And we actually, so this is not the complete diagram because we also have the inner core, which is again a solid. So this function would actually again go up to a non-zero value, but because of the liquid outer core, we sort of have to compute the toroidal modes of the oscillation of the inner core separate.
I would like to invite Ayanda for his presentation and ask Hariom to begin with his presentation.
You might see some familiar names in this presentation too. The paper I'm presenting is written by two alumni of St. Stephen's.
Is this Sanjay sir?
Sandeep Krishna and
Sandeep Krishna.
Akshay Goyal.
Akshay Goyal, biological.
Biophysics, both of them are in biophysics, right now at CDS and CDS. So
Akshay derived
नहीं नहीं ICTS हाँ NCBS क्या था
from He's the one who also won the
जिसको वो जल्दी चाहिए
He's also the one who won the Meera.
हाँ उसका वो वाला था नहीं audit diagnosis
Hi, my name is Ayan, physics major, biology minor, and I'm presenting a paper not written by me, but by Akshay Goyal and Sandeep Krishna, as I'm working with them in the coming year on my thesis project based on this work. So they studied the chemical basis for metabolic interdependence in microbial communities, and you might be wondering why I'm presenting this as a physics project. But I'll get to that. You'll see why. So one interesting statistic about microbial communities is that 99% of microbes which are naturally occurring cannot be cultured in the lab. The moment you take them out in isolation, they die immediately. And the reason, one of the proposed reasons for that is because they form these complex cooperative and competitive interactions with each other, which they require for survival. And one of these is something called cross-feeding, where essentially one species requires a metabolite from another. So say A produces a metabolite alpha, which B requires for survival, and then B produces a metabolite beta, which A requires for survival. And if either of these are not in the presence of each other, neither of them can survive. So essentially the question that they are trying to answer in this paper is why is this cross-feeding so evidently preferred over just having an autonomous cell which can produce all the necessary biomass precursors in order for survival to happen. There seem to be several clear advantages. You are dividing the work of doing the metabolism between the cells of the community, and these interacting cells seem to have higher growth rates as well. So they're trying to understand why that may be the case. And this is where they try to use a more physical approach. So what they have done is they've tried to look at the metabolic networks inside these cells. And there is a vast wealth of knowledge in something called the KEGG database, which is essentially a database of all the chemical reactions that take place inside a bacterial cell. And this is like decades worth of work. And in this space, they have tried to map nutrients to something what they call biomass precursors. And those biomass precursors are essentially all the chemicals that are needed for a cell to survive. And they've assembled all these randomly assembled networks if they can. And now they've analyzed that ensemble to check whether they're viable or not. They've given certain viability criteria, which I will go over in a bit. And then they've said, okay, now we have these autonomous networks. Can we merge them together and create interdependent networks? So now you have interdependent and autonomous networks. And then let's measure their efficiency and see whether the merged networks can perform better than the autonomous networks. And if you can show that even some of these merged networks are performing better than all of the autonomous networks, then you've essentially got a working explanation for why cross-feeding is more beneficial. So this is what the KEGG database looks like. It's So it's a horrible and extremely complicated network. Each of these points is a chemical reaction. Each of the links between them, each of these points is a molecule, and each of the links between them is a chemical reaction. And this is the space they were working with. So they identified the nutrients on this, they identified the precursor molecules, and then they thought of all the possible networks that connect them. Right? So how do they go about this? So say these are your nutrients. These are your biomass precursors. You consider all your possible networks. And then they applied something called a viability criteria. What makes a network viable? So they started with these. They just had two nutrients, acetate for carbon and ammonia for nitrogen. And they had certain currency molecules, as they're called by biologists, which are molecules that are always present in the cytoplasm of a cell. And then they said that every network, this is an example of a viable network, every network must produce all the possible biomass precursors required for survival, for an autonomous network. And any network should also be a minimal network. A minimal network is one in which if you remove any one of these intermediate molecules, then all the biomass precursors cannot be created. So it's essentially you're removing all the redundancy from the network. And lastly, they essentially created merged networks, which was done by so you create an autonomous network, you prune off all the unnecessary redundant branches, and you're left with a minimal network. And then this minimal network has certain byproducts. And they said, now what if you take this byproduct and provide it to the second network over here? Could that be used to remove a pathway? So now this byproduct is allowing cell B to produce precursor 2. So now it no longer requires this pathway over here. So now both of these networks are interdependent. If this exchange of byproducts is not happening, B won't be able to produce 2 and A won't be able to produce 1. Okay? So now you have merged networks and you have autonomous networks. How do we measure their efficiency? So the efficiency they measured on 3 counts. One was how big the network is, which is essentially the number of reactions. How much energy yield they produce. So this was measured in terms of how many molecules of ATP and NADPH. These are molecules which essentially are used as energy currency inside a cell, are produced per nutrient molecule, and how much biomass precursor was produced per nutrient molecule. And these are the distributions which you see for an autonomous network. And this, right now, it just tells you what the ranges are for an autonomous network. They did the same then for a merged network, and they found surprisingly that this small percentage of the merged networks perform better than all the autonomous networks. So if you see over here, the energy yield for the autonomous network, the highest performing one is around 4. And beyond that, you have some networks which are merged, which could produce even higher energy yields, and similarly for biomass. So essentially, you can say that these obligate cross-feeders, which are essentially dependent cross-feeders, can outperform even the most productive autonomous networks. So what is it that makes an outperformer? So there are a few things. One thing they noticed was that when they saw the merged networks, the networks that were outperformers tend to be the ones that had an intermediate amount of similarity between the networks. If they were too similar or if they were completely different, they would not be outperformers. And we'll see why that's important in a second. And the second thing is that they had something called choke points, which were more in number and they were located earlier in the network. I'll explain why both of these things are important. And to do that, we need to understand what a choke point is. Now, choke point is something which we might have seen in another in physical systems too, but it's essentially the reason a choke point happens is it's got to do something with a non-linearity in the flux of the network. So the flux is, say, the speed at which a network is processing its metabolites. So say network 1 has this much flux and 2 has this much flux, then the combined flux of this, once you merge them, is not equal. So it's not just a linear superposition of the two initial fluxes. And this non-linearity has to do with the fact that the flux of reaction is limited by the flux of the reactant which has minimum flux, which means that essentially you can think of it as the limiting reagent in a chemical reaction. If you have like 3 reactants and one of them is being supplied at the lowest rate, the total rate of the reaction will be limited by that reactant. And a choke point occurs when essentially when you're merging the networks, that limiting reagent is changing. And when that limiting reagent changes, your total metabolic flux is changing. And that is what allows the merged networks to become outperformers. That is what is giving the non-linearity to the flux. And what they found was that the networks that have intermediate overlap or intermediate similarity tended to have a lot more choke points. And that's why now the intermediate overlap makes sense. And also the choke points tended to be earlier in the network. And the reason that is important is if you are speeding up a reaction earlier in the network, then all the following reactions will also be sped up. So there's a downstream sort of cascading effect. And that makes the precursor molecules be produced at a faster rate. So that's why the outperformers tended to have their choke points before the exchange even happened. Whereas the non-outperformers in red over here tended to happen later. But this isn't the whole picture. Right now the flux is non-linear, but it could increase or decrease. And if it decreases, then obviously you're not going to be an outperformer. You have to have a non-linear increase in flux. And the way we can ensure for that is what they call donor and acceptor quality. So when I'm merging a network, what we are essentially doing is we're taking a network and we're saying, okay, this byproduct is being formed. Let's remove one pathway which is going to one of the precursors. Now, this byproduct will be produced in a different quantity. Now, if this change in byproduct production is positive, then it's something called a good donor. And if the change is, when you add another byproduct from another cell in, then the biomolecule precursor also may increase or decrease. And if that change averaged over all the byproducts is also positive, then it's a good acceptor. And then they found that all the 96% of the outperformers were both good donors and good acceptors. So this was our third and final condition, and that essentially gives us 3 necessary conditions, but also nearly sufficient conditions, because they found that 80% of the outperformers satisfied all these 3. They found that the choke points should exist, so that there's a non-linearity in the flux. There should be an intermediate overlap, because if you had 0% overlap, then there would be no common reactants, and therefore there would be no improvement as you merge. But if there's 100% overlap, then you have exactly the same reactants, and therefore again, you would have no increase in flux. So you need an intermediate overlap. And you need to be a good donor and a good acceptor in order for the nonlinear increase, for the nonlinearity to be an increase other than an increase. And these are a few questions that I want to be looking at in my thesis further. So real metabolic networks, real microbial communities are far more complex in this. Here we have only considered pairwise versus individual interactions. This is what like a normal microbial community looks like, where these are all different species with different interactions. So what would it look like when you had 3 or more interacting microbes? How could these networks be constructed? What if the networks had redundancy to them, where we consider only minimal networks? What if the molecules being produced are expensive, where It's not just byproducts being exchanged. And how would these evolutionarily evolve from autonomous to merged networks? And finally, a more biological question is, there's a theory of endosymbiosis, as it's called, where mitochondria came into bacteria and formed eukaryotes. So could we explain the sort of a symbiotic relationship with this one? Thank you.
I don't have a very direct question related to that, but when you have you ever abstractly look for the networks, we have just a simple basic network works. I mean, there is a very interesting phenomenon in which there is actually phase transition happening. As you were suggested that there are independent networks, and then there comes a time, let's say there are small chunks that are connected, and then there comes a transition at a period or at a special number of connections in between those nodes, that there is actually a sudden jump from these independent colonies to a very great connected. That is a loss-ranging phase transition. I'm just discussing about the ideas, and what I was thinking is mostly about that the interdependency of different kinds of different networks and how one is connected to the other. The survival of the one and it's connected to the other, and that actually lead us to predicting how life in its initial stages started as an autocatalytic process. In a sense, it starts from something, let's say a broth, a normal broth, and then there are different independent reactions that are catalyzing themselves to create at the molecular structure or what kind of reaction that goes on. So that is just a discussion. That's it. No question.
You talked about redundant networks. What are those redundant networks? How do you remove them to get those minimal networks?
So, so if we see in this sort of a construction, you could get from here through multiple pathways. Now, this molecule may not require this molecule to be present in order for it to be produced. And therefore, you could remove this molecule from the network altogether and the pathways that connect to it, and you would still be able to produce this chain of reactions. But now, once you get to this point, any further removal would mean that, like say if I remove this molecule, then this one would not be produced. And now you would not be able to get the biomass precursor. So, and your viability criteria says that every network must be able to produce all the biomass precursors starting only from nutrients and currency molecules. So, a minimal network is essentially one where if you're only provided with these, can you get to this, and any further removal means that you can no longer get to it.
So earlier when you tried all the possible
Yes.
connections between all possible molecules that you have.
That's why, I mean, this was after the pruning. They got 19,000.
Do you take any physical considerations while you remove this, or really, if they are chemical reactions, what is the probability of those reactions? Or is it just seeing that, removing that doesn't affect your final product?
So, because they're not trying to optimize for something, they want to consider the entire space or the entire ensemble of possible networks and then see which ones are more biologically plausible. Which is why they did not take any such consideration initially.
When you say plausible, so what consideration you will find out which is more biologically plausible?
So, for example, only the networks which are more efficient than all possible autonomous networks are likely to be
the
outperformers are likely to be biologically selected by natural selection, say, over an autonomous network. So if you're running an evolutionary simulation, you would expect these ones to be selected. But if they were in this range, then maybe they wouldn't be selected because they're not as efficient as the autonomous networks.
And what is the maximum size of the cluster that is created by this two-body start?
I am not actually sure how large these networks were. In all the graphs,
with two and then it forms a cluster.
right.
So, should there be a maximum number for one cluster and then it breaks into another cluster of a similar size, or it will keep on accumulating to bigger solutions?
So right now for this, they have only considered singular autonomous networks and then merging them into pairs. They haven't considered if you were to merge more networks and form more complex communities. But in theory, you could find ways
So
to do
even if two come in or two initial, because when you're making a community now with a cluster. This cluster can keep on growing or can break up into smaller clusters of a particular size.
So because we're considering minimal networks, we know we're dealing with the smallest possible networks that we have. If we made them any larger, then there would be redundancy in them. And therefore, there is a sort of a limit in that sense, but I don't think that's something we do.
Yeah, just in short, can you just explain what is an autonomous network? Just in short.
Yeah, sure. An autonomous network is essentially a network where starting with these molecules, you are able to get to a predetermined set of biomass precursors, which is a biological, like a list that they have made that cells need these to survive. And this is an example of one. Where you're starting with only those, you're producing all of them. If it is not producing even one of them, then the cell cannot survive. And therefore it will become dependent.
So autonomous is product related.
Yes.
It will be what energy you supply or what kind of energy you use. It doesn't really matter.
I would now like to invite Harun to come.
हाँ मैं रह जाती हूँ घंटी पहले बजा देते हैं
नहीं तो तुम वहीं से स्टार्ट कर लो ना, इसको बाद में लास्ट में कर दो।
हाँ मैं सबकी बात ऐसी ही करेंगे तुम सारे दिन ही चले मुझ पर क्यों बताते हो
After the break, you should have started.
नहीं एडवांस पढ़ जाके हम एक्स्ट्रा काम नहीं करेंगे एडवांस पे क्यों पढ़ेंगे बैठ के सब यहीं पे बता दो
क्या हो रहा है? I'm okay. And actually, I'm okay with it. But people are
मेरा भी कुछ है नहीं जब भी खाली हो जाए इसको भी होना चाहिए मैं चाहती हूँ
कितने बजे मंडे ये फ्री व्हाट इज योर शेड्यूल मंडे टाइम टेबल
मंडे के दिन
मैं देख लेती हूँ एक मिनट
मैं टाइम टेबल के लिए खाया वगैरह बनाएंगे तो लैब है क्या देखो सभी में मैं 11:30
10:30 से 11:30
मैं 11:30 के बाद
11:30 पर हमारी लैब है फिर आपके 11:30 से
12:30 आपके साथ लेकिन एक्चुअली एक तक हो गई आप
हमारी कौन सी लैब अकेले अकेले
आपके साथ आप लोगों ने बैठे ये भी रैप है रेखा भी फ्री होगी रेखा फ्री होगी
हाँ हो जाएगा यार।
फ्री है तो सालवार या उसकी बेसिस बटे तो उसके आगे साथ
आपकी उसकी शायद एससीसी
नहीं
श्रुति श्रुति के साथ
दोनों में से एक जना को आ सकता है श्रुति को ऐसे तो मुझे नहीं लगता कि वो घर जाना है मेरा ऐसा प्रॉब्लम है साल बार को देखा क्योंकि सारा टाइम हरिओम की प्रेजेंटेशन में से कट हो गया
मेरी गलती नहीं है।
लैपटॉप की वजह से
लैपटॉप की गलती है।
से लैपटॉप एक ही क्यों नहीं कनेक्ट करते
तुम बोलो तो मेल कर दे।
सब
तुमने मेल कर दे।
-30 हो गया
Hello everyone, today I am presenting some work which I have done in condensed physics. It's in topological insulator. So before we going dive in deep concept of topological insulator, let's talk about what is topology first. So topology is about it's a branch of mathematics which talk about an object if the object is continuously deforming to another state, its the property remains unchanged. So here we can see that the cup is deforming to donut, but there is something topological invariants which are not changing. And what is that topological invariants which not changing? I will talk further. I'm sorry. and you can see the letter cannot be deformed.
the topological
Laddu cannot be deformed into jalebi because we need injured hole. And let's talk about what is topological invariance. It depends on our system. That for example, if I calculate flux of any charge, that the flux does not depend on surface. It depends on the strength of charge. So here in this system, the topological invariance is the strength of charge. And further, I shown you a donut example where the number of holes is unchanged during the continuous deformation. So here the topological invariance, how it leads to in our experimental data, I will show you further. Before we going, so the question is, what is topological insulator? It's a special material in condensed matter physics. It's like it's bulk in insulator, but has metallic property on the surface. So is all the samples which have surface metallic, they are topological insulator. For example, this is sample which we have created in the air CB. So it's not a topological insulator. Why this is not topological insulator? Because it does not have topological invariance, which I will talk further. So let's see. There is topological invariance which when it's arrive, I will talk. I will demonstrate further. That first I need to demonstrate what is quantum, how the quantum Hall effect leads to in topological insulator. So when electrons move in 2D, and if we applied high magnetic field in low temperature region, then the resistance behaves very interesting behavior. So here we can see the longitudinal resistance is sometimes 0 and sometimes non-zero. But the whole resistance are quantized because lambda levels. So here the resistivity is sometimes 0. It leads to electron flow without energy dissipation. That's the point of our topological insulator. Say that they can allow to flow the electrons without any energy dissipation. But the quantum Hall effect is not practical. Why? Because it needs large magnetic field which and low temperature region. So that's why we need another solution, which is quantum spin Hall effect. How the quantum spin Hall effect works? It's like it's use own spin orbital coupling and it's create intensive magnetic field, and that leads to it the phenomena same as quantum Hall effect. So this is quantum Hall effect. Since there is no external magnetic field now, we created this phenomenon by using self spin orbital coupling. So there is no magnetic field, and the time reverse symmetry is conserved. And this is very insightful statement. The time symmetry conserved in this system. And if I talk about what is topological invariance, this is a topological insulator actually, because its edges has metallic property in both system, but the bulk is insulator. So if I talk about what is invariance here, the first is conduction band. The conduction band at the metals, it's connected with each other by two that spins dispersion line, and at the bulk is behave like insulator. This is the type of topological insulator. Now the problem with in our hand was we have a sample of tin tellurium, and we worked on that is this topological insulator or not. So how we deal with problem? So first we have to check, oh, if this is real sample which we are talking about. I did SRT analysis, and I found very interesting physics this Miller indices, and calculated lattice parameter, and which is approximately very near to this expected value, and the references I mentioned in my report which I have given to you. And then we go to our next step. To make topological insulator, we need spin orbital coupling, and to verify is the sample is have spin orbital coupling or not. So we need we use transport property behavior. If there is two types, localization, delocalization. What happens in localization? The probability get maximum when the electron come back scattering. It's like I have shown the mathematics in my report. You can refer to that. But it's like initially the electrons are localized in material, but if you apply some internal spin, it's like vector potential or spin orbital coupling, but they can delocalize. It's called anti-localization. And how this works is like the conductance in the quantum diffusion region is relates to probability. So going here to here, its conductance is directly proportional to how the probability is you have. If the net probability is 0, then conductance would be very low. So in anti-localization, the P net is 0, and the effect of magnetic field is very weird. It's as shown here. In our data samples, we have what we have seen, the magnetic field affects the resistance. It's got saturation, and this is effect happening because of spin orbital coupling. So there is three nice guys who did their model, and we use this model to find whether it has spin orbital coupling or not. So to sample have spin orbital coupling, the alpha should be minus 0.5. So here in our case, the alpha is coming out minus 0.5, but in higher temperature is not minus 0.5. So why this is happening? Because the weak anti-localization does not hold for on high temperature. So the questions remains same. Is it topological insulator real? So it's not, because for topological insulator with spin orbital coupling, it should have metal in bulk should have insulator. So here in our case, what we have found, the bulk is not insulator; it's behave like metallic. But there is interesting phenomena because with different thickness, what we getting different resistance, like changing in resistance with temperature are different. So why this happening is initially we were not sure why what's going on here, but then we scroll. I scroll some research paper and I understand what is happening in low temperature region. There is present weak interlocalization or either electron scattering. So the based on I have found this model. I have mentioned the reference, and if the slope is positive, then well effect is dominates. But if the slope is negative, then electron scattering is there. But we for the 30 nanometer we found electron scattering is there, and for the and we have the upturn is there, and I also try to explore why this upturn is occurring, because and I found in some other reference that it's occurring because electron and photon scattering. So I have used this model to with my experimental data. So what I expected is here. This is my expectation. I got this value, and so this is so we have seen that bulk is not insulator because the resistance is getting high at high temperature. It's behave like metals. But real insulator, how real insulator does? This resistance is measured by 4-probe method. So the 4-probe method, the both surface and bulk currents are it leads to create resistance. So what is happening here in high low temperature there is well effect is there, and but high temperature the suddenly is the resistance is decreasing. At 4 degree, it's mean at around the room temperature, the resistance getting very low. In the surface states dominates. It's not from bulk states. So hence we found that our sample is not topological insulator.
Very good, sir. I just want to know one thing: what is the role of spin-orbit coupling in your? I could not understand the importance of spin-orbit.
For me, I also cannot understand because it's need a lot of mathematics.
No, you're not getting me. I'm not asking you what is spin-orbit coupling. That okay, you don't know. I'm just trying to
It's like
understand.
yeah, I tried explore that. It's like when the spins are can be any direction, but there can be make any situation is like the spin is locked with orbital motion. It's like the all spins are if they get same direction, then it leads to total dipole moment, and they can create intrinsic magnetic field.
Okay, right. That's what I wanted to speak.
I want to ask you a very simple question. How does the introduction of magnetic field, make the system lose time reversals and
Okay. So it's like when we have magnetic field, if we if I think about classical mechanics, then let's this is an electron, so it's in magnetic field, and if it's going to in any direction, and so time, what is time reversal symmetry? If I change the t to minus t in the system, so the force will be changed because the velocity is getting changed, and the velocity from the magnetic field is to v cross b. Now the changing the time is changing the reverse, because the reverse system the force is acting on different direction. As the if we apply in this direction the force and magnetic field, let's suppose in this direction, then the force magnetic field be the magnetic force will be in this direction. But if I see the system in my t to minus 3, then the force will be other direction. That leads to breaking time reversal.
Is there any example of blockage of time reversal simply?
Yeah, quantum. There
That is an
is.
example of breakage of time reversal.
Yeah, yeah.
Right,
Quantum.
right.
But in quantum.
Okay, then that's fine. Okay, just tell me, how are you reaching the temperatures of 0.3 Kelvin?
Essentially, where there is. I do not like. Can be like. By.
Even in thermodynamics, how do we get to lower temperatures?
It can like by freezing crystals and.
And that works at 0 degree or minus some degrees, but the temperatures in Kelvins, like 2, 4, 10.
Very low temperature.
Very low
How do you
temperature.
attain very low temperature? What phenomenon? Can we use magnetic field?
मारेगी मैम ने बड़ा मैं अभी बात
चलो ठीक है चलो ओके
Would you like to invite Samana for a presentation and ask Ravi to get this started?
बम ही मार दिया पूरा।
उसको डरा दिया मैंने ही डराया सुपर फास्ट स्पीकर से बोल मैं डराया
जो कैमरा रिकॉर्ड हो
ये पढ़ के
अभी तो मैम को वाइवा लेना है थर्मोडायनेमिक्स से स्टार्ट
इसमें से
ये जो इसमें पढ़ने के लिए नहीं है
Hello everyone, I'm Sahana and I'll be presenting on synchronization in coupled chaotic systems. That's a mouthful, but we'll get into that in detail. So this is based on the work I did with Prof. Ramaswamy at IIT Delhi, and while I was exploring chaotic systems under him, one of the papers I encountered was related to synchronization of chaos in such kind of systems. So what exactly do we mean by that? So first off, what kind of systems are we studying here? Now consider dynamical systems in general are defined by differential equations. So for example, a couple oscillators. But these systems are often continuous. What we're looking at here are discrete systems because they're not studied very often. So for example, take your simple cosine function and say we have an initial value and take a calculator and just add in your initial value to the cosine function. Whatever output you get, try to put it again and again and again. And whatever value you get, say you record it like x0 is whatever you've chosen, then x1 is your second answer, x2 is your third. That can model the orbit of your system, basically the trajectory of your system. That is what we call our 1D map. And that's what we're going to study here. But in our case, we have two 1D maps that are coupled with each other. So essentially, we have a 2D system. So, and many of these, 1D maps show chaotic behavior. But what exactly do we mean by chaos? So you might have heard of the so-called butterfly effect, where the clapping of a butterfly's wings might cause a hurricane somewhere else across the globe. That is just an example of sensitivity to initial conditions, and that is a marker of chaos in a system. And then, but then, like, we are physics students and we like to quantify things. So how do we measure chaos in a system? That's where these so-called Lyapunov exponents come in, and you can think of it as a way to measure chaos in a system. Finally, what the kind of specific system we are seeing here in this paper is the coupled logistic map. So a logistic map is a one-dimensional map, as we have described earlier. It's a one-dimensional discrete map. This one's supposed to be 1 minus x, but yeah. So what we're going to study here is two logistic maps that are kind of coupled with each other by coupling parameters. And in the paper, the generalized coupled system is defined this way. So what we just did is take the logistic map system. We've taken A to be 1 because it's easier, and we've taken R, which is our rate of population growth. Logistic maps are generally used to monitor population growth. And we're taking that as 4 because usually at that threshold it shows chaotic behavior. And when we plug it in, this is the system we are working with. Now, first word in our presentation, synchronization. What exactly is it? So basically, synchronization refers to a strong correlation between the system states. So these are usually modeled by network of interacting elements in the system itself. So for example, you can have neurons that are firing together in your brain, or you can have coupled oscillators that are moving in phase. So those are examples of synchronization. Now we'll come to what we mean by weak and strong synchronization. Now, as I mentioned earlier, chaotic nonlinear systems are defined by the butterfly effect. But this kind of defies what synchronization actually means, right? Because synchronization is something we associate with stability, with order. So what people have found out is that coupled systems with some sort of a symmetry, it could be symmetry in the parameters, it could be spatial symmetry, these show chaotic motions that eventually get synchronized. And conventionally, synchronization, as I mentioned earlier, is when the coupled states kind of match each other as the entire system evolves with time. But what we're going to look at over here is called generalized synchronization, where the states are related by a particular function. And over here, it's usually a smooth function, smoother differential function. So this particular system, the coupled logistic map system, is essentially a unidirectional master-slave system. So your xn plus 1 is the master system, your yn plus 1 is the slave system, and the xn plus 1 is driving the slave system. But the reverse cannot happen. That's what we mean by unidirectional. And so over here, your synchronization is marked by the transition from an unsmooth map, because the x and y are related, to a smooth map. And what we mean by that is that initially we are starting out very small, so the values are pretty close, our initial conditions. And as it is you know, so what we mean by an unsmooth map is that because basically they are not differentiable because of the fact that you have an abrupt change because it's initially very chaotic. So because of the small change, you have a very abrupt effect and therefore it is unsmooth. But eventually when it synchronizes, there is stability. So it becomes more, the system becomes more predictable and therefore the mapping becomes smooth and continuous. And so what we have also defined a particular auxiliary system Y prime in our couple logistic map, and that is to study the intermediate dynamics in the system. So we don't want to just see the final result, we want to see what happens in between. So that's where weak and strong synchronization come in. Weak synchronization is marked by the synchronization between your initial the master system and the slave system and the intermediate auxiliary response system, and your overall your strong synchronization is mapped by the overall synchronization between the original master and slave system. So that's what is that's what we're going to study here. So the first thing we do when we want to look at any dynamic system is to model the dynamics on a phase plane. And that's what we've done here. So we've taken three different k values. So this one is for k equals to 0.1, and we saw what the dynamics look like between x and y, which is your original master and slave system, and y and y prime, which is your slave system and the auxiliary response system. And this is what the phase portrait looks like. And we can see it's not synchronized at all. And as we increase the value of k, this is for k equals to 0.4, we see that there is some sort of a synchronization between y and y prime, right? Because they're matching. But over here, it's still not yet synchronized. And finally, when we suddenly increase it to 0.6, we see that both of them are matching. So this is what we define as strong synchronization. But when, at what k values do we actually see this sudden transition, right? In chaos terms, this sudden transition is also known as a bifurcation. So at what k values do we see? So for that, we explored the Lyapunov exponents for this system. And in our case, since we have a couple of systems, fancy term for the Lyapunov exponents, just conditional Lyapunov exponents. Since we are dealing with a 2D system, we will have two Lyapunov exponents. And the thing about Lyapunov exponents is that the greater it is, the more positive it is, the more chaotic the system is. And if it's negative, it means that the system is stable. I will not go into this right now, but this is basically the algorithm to find the Lyapunov exponents. So the two Lyapunov exponents we have in our system are basically called conditional Lyapunov exponents and transfers. So conditional gives us the Lyapunov exponent between y and y prime and tells us about the stability between y and y prime. Transverse Lyapunov exponent gives us info about the stability between x and y. And we can model, we can just find the Lyapunov exponents using these equations over here. So what I did was for 1000 k values between 0 and 1, I tried to generate the Lyapunov exponents for a trajectory, and I plotted it on Python for this particular system. And we want to find a threshold at which this this transition of bifurcation occurs, right? So usually it's marked by some change in the sign of the Lyapunov exponent, so that's why it has to cross the x equals to 0 axis. So we found two particular thresholds. This one is around 0.3, This one's around 0.5. And this is therefore a weak synchronization threshold. This is a strong synchronization threshold. And I tried to plot the derivatives also to see how it varies against k. So we see that when it's unsynchronized, there's a huge variability, and then after your 0.3 threshold, there's slightly less variability, and suddenly at 0.5, you can see that it just goes negative, and it just keeps going down. So that indicates stability in the system. Now, I wanted to see why we have these particular, threshold values. So I also looked at other systems like sine map and the cubic map, and also, more importantly, the 10 map. And I found the 10 map pretty interesting because when I tried to model the Lyapunov exponents for this particular coupled system, they actually matched the coupled logistic systems Lyapunov exponents. Even though it's different, they're pretty much the same. And when I tried to see the dynamics, they actually pretty much match. So that is something I found very interesting. And when I did a stability analysis, where I wanted to find the fixed points and see if they were stable, unstable, or periodic, there were 4 fixed points, but the last one is particularly important because you have a negative eigenvalue and a complex eigenvalue. And typically, negative usually indicates stability, but a complex one indicates periodicity. So when I try to find out, so there are very static bifurcations, and when I try to find out what kind of bifurcation that 0.5 strong synchronization threshold was, we came to the conclusion that it's probably a Hopf bifurcation. So basically, it's in one direction, it's stable, and then it's also periodic at the same time. And this is the last one. So things to further look into why computationally figure out why we have this Hopf bifurcation. Because when I tried to find the bifurcation map, it didn't make sense. It's in the appendix. I can show it to you if you really want. And also explored generalized coupled logistic map system and basins of attraction, for example, a little more. And in fact, I have been process of that and generated basin of attraction for one. So mu here is essentially equivalent to your rate, and your epsilon is equivalent to k, which is your power. And thank you.
So a very simple representation. Just tell me the trajectory of a phase point for a chaotic system. I mean, just take a small region in a phase space and just tell me the difference between a simple system, like what you're doing to this trajectory in the phase space versus a chaotic system. Let's say it's a very small finite region, not just a single point, but a very small finite region around it. What could be the both differences?
Okay, so we can take the example of the logistic map itself. So when you want to plot the so if you want to plot for a logistic map, so you have x n plus 1 equals to your rate, your combination x n 1 minus x, right? So typically, it's if you want to plot the phase portrait, x n plus 1 and x n, it would look something like this, right? Where you have between 0 and 1. This doesn't, I mean, you can't see chaos over here clearly. So to visualize chaos, we actually vary it against the parameter r. So that's where the bifurcation map comes in. And when, in fact, I have it here, if I go to, so this thing over here, it's not very clear, it is actually the bifurcation map for a logistic map. And what we're doing here is we're varying x n plus 1 against the parameter r. And over here, what we see is, so if I want to do that, if I say divide it into various parts, say we observe this particular part, we would initially see something like it, going like this, but then it eventually settles to a particular point. So this could be, say, r is less than 1. Now, if suppose you want to explore even higher than that, we see something called period doubling. So that means your population basically varies between two different values and goes like this. And then as you increase your R value, you will see a like a 4-period doubling sort of a thing where it varies between 4 different populations. And after a particular R value, you will see that the entire process just randomizes, and that's where we see chaos. So that's what happens here. So over here, what is happening is your period doubling, and then you have a 4-period doubling, and then it just becomes chaotic over here. So that's how we visualize chaos in such systems.
My question is related to about the momentum and velocity space, but that's
Oh.
What is a coupled tent system?
So we have the tent map here. Yeah. So this is how a tent map is generally defined. We just put it back into the general coupled system that is defined by the paper. This one. Right? We just plug the tent map over here, and eventually what we did was we modeled it and we found the Lyapunov exponents and plotted it.
For the two thresholds that you decided. One
Yeah,
and
for
one weekends.
You talked about both the bifurcation. You concluded that it's the hope bifurcation, and you also talked about the period doubling.
Yeah, period
on the,
doubling, yes.
on the basis of limit cycle, how would you differentiate between two, hope and the period doubling?
So, on the basis of
Limit cycle.
So over here you can see that it settles to a single point. So you can say that this value. So over here I have marked it. But basically, for r less than 1, it goes to 0. So that will be 0. Your population basically goes extinct. But yeah, the point is, you don't actually have for such a system you don't have a limit cycle because it's a chaotic system. So you don't unless there's an attractor, you won't really have the limit cycle.
And for the last presentation of the day, I would like to invite
problem is.
Why is the remote? Yeah. Yeah. Green blink.
Hello everyone. Last presentation, so you can read this out for you. But okay, so I'm Pallavi and I will be presenting on testing the performance of an RR lighting lighter template fitting algorithm. Sounds like a lot, but I will break it down for you. This is the summer project I carried out at University of California, Santa Cruz under the guidance of Professor Radha Gupta there. Okay, so I want to clear this up. The algorithm that is mentioned here was developed primarily by his PhD student Liu Feng. My job in the summer was to basically classify the bias in the algorithm, which I will explain. Okay, to begin with some background, a galactic halo is a roughly spherical extended region surrounding a galaxy, which consists not only of visible matter in the galaxy like stars or globular clusters or other dust or other things. It also consists of the dark matter surrounding the galaxy, which we know is invisible but has some gravitational influence. Now, a question we can ask is, what is the extent of the galactic halo surrounding a galaxy? To answer a question like this, especially for our own galaxy, the Milky Way, we look at these stars called the RR Lyrae stars in the Milky Way halo. Now, these stars are not your typical stars like the Sun. They are periodic variable stars. What I mean by that is, let's say you go out tomorrow. The sun will be giving us the same intensity of light today, tomorrow, 100 years from now, a million years from now. But these type of stars change their intensity of brightness with respect to time. That's why they're called periodic variable stars. And because the cause of this variability can be for many reasons, but for RR Lyrae stars in specific, these stars are not in hydrostatic equilibrium, which causes them to expand and contract, varying their brightness with time. Right? Now, these stars have a unique period luminosity relationship, which means that even though they vary, their luminosity varies with time, their time average luminosity in a specific filter is very well known. And because that relationship is very well known, we can know the distance to these stars using the inverse square law. And once we know the distance to these stars, like we can know very precisely the distance to these stars, which is what makes them excellent standard candles. Hence, we can use them as tracers of the Milky Way halo, because these stars in particular that we're looking at are situated like very far away from the galactic center. They are the most distant stars known in the Milky Way halo. So we can use them as tracers to find the extent of this dark matter halo surrounding the Milky Way. The data that we used was from the next generation Virgo cluster survey. Now, this is typically what an RR Lyrae light curve would look like. A light curve is just time on the x-axis and the brightness on the y-axis. So you see the brightness varying with time. And this is typically what, for an RR Lyrae, this is what the light curve looks like. However, the data that we worked with looked something like this. Very sparse data collection, as you can see. Again, you have days on the x-axis and brightness or luminosity on the y-axis. The different colors represent the different filters that the data was collected in, which is mentioned here. The bands, the different bands are U, G, I, and Z. Ultraviolet, green, far red, and further red. Now, yeah. So how do we go from this to this? Is a process known as phase folding. Now, phase folding is just going from an unfolded light curve, is what we call here, to a folded light curve. We just change the x-axis from days to phase. Now, when I say the word phase, you might think of phases of the moon, right? So, if the moon is a half moon today, you'll say that the phase of the moon is half or 0.5, right? So, it's completed half of its period. So a phase is just a fraction of the period that's been completed by the object. So to go from days to phase, we use a formula where phi is the phase, p is the period, t is the range of days that the data was collected over, and phi naught is some phase shift. Now, to find, now because there's so many stars, we use a light curve template to model the light curves of these stars. And the template model has a form of this. So you have parameters like the amplitude, the period, the peak brightness, the phase shift, the actual shape of the light curve. The shape of the light curve we already have some idea because of empirical RR Lyrae light curves from earlier data sets. We generally know what the shape of an RR Lyrae light curve would generally look like. And all of these parameters are also dependent on the different bands, the U, G, I, and Z bands that the data was collected from, right? So, the main point I'm trying to put here is that there are 14 unknown parameters, but only 30 data points for each star for us to model them, right? Which brings us to lots of uncertainty. For example, for this star, this particular star, the data was collected roughly over 3.5 years. But RR Lyrae stars typically have very short periods of half a day or less than that, which means that even if the period that our algorithm was estimating, even if it's off by very little, it could lead to a very bad light curve fitting. So if you look here, this is a graph called a periodography. On the x-axis, we have period in days that the algorithm would estimate, and on the y-axis, we have a score of the fitting. So the higher the score of the fitting, the better that period is for the light curve model. Now, this graph is zoomed in. It's zoomed in at one of the peaks here. So a peak would mean that it is a good fit for, because a peak would mean that it's got a higher score, which would mean it's a better fit for the light curve. But even when you zoom in into the peak, you see that it's very irregular. Even if the period is off by as little as 2 seconds, we can produce, like, the algorithm would give out a completely different fitting for that period. So these are the uncertainties that the algorithm had, and because of that, we naturally observed that there was an observed clustering of phases for particular types of stars. So RLI are of many types. We were working with type AB and type C stars. In type AB stars, we noticed that the phases were clustered between 0 and 0.25. And there was a lack of phase coverage beyond that, especially in these two bands here. So we realized naturally that the algorithm had a bias. So our job was to classify that bias, and we worked with 180 RLI from the NGBS catalog, the Next Generation Global Surveys catalog. So we worked with 180 candidates of RLI. And the methods that we used were pretty simple: probability distributions and cumulative distributions, to figure out exactly which parameter did the bias depend on. Was it the amplitude? Was it the different bands the data was collected in? Was it other things like the magnitude of the star, the peak magnitude of the star that the algorithm was estimating? So, if there was no bias in our database, so there's a assumed uniformity that we're working with, because the star doesn't know when we're taking its data, right? So there should be, in the input, there should be no bias for the phases. So if there was no bias, a probability distribution would look something like this, and a cumulative distribution would look like this. However, what we observed, now this is when we classified the data into different bands, U, G, I, and Z. We observed that there was a clear deviation from what the black dotted line is, what we would expect if there was no bias. And the blue line is a clear deviation from that result. So especially in the U and G bands, for I and Z bands, it's not by a lot, but the deviation is clearly there in U and G bands. So we figured out that yes, the bias in the algorithm typically depended on the phase on the filter that the data was in. So why is there a bias? I will go over this very quickly because I don't have much time. But because because there were so many unknown parameters, to reduce the degrees of freedom, we put some restraints on those parameters. And because of these restraints, we realized that the algorithm ended up overestimating the amplitude. So this overestimation of amplitude was caused because of the restraints that we had. To fix that, our idea was to let the old algorithm give us an estimation of the period. In that period, we would do a grid search of 2 seconds before and after and see if we could get a better period around that. So we did a grid search of 2 seconds in that range, and yes, and we released the constraints only in that range of 2 seconds, and with the new fitting algorithm, so this is the old one, and for the same star with the new fitting algorithm, we could see a clear, you see that the amplitude is much less exaggerated. The problem of phase coverage around here has also been solved by a little. This can be seen here. The magenta line is with the new algorithm. And yeah, so it's not the best, but there is clearly an improvement seen here. And yes, this is the reference, and
I just have one question. question about when you said about standard candles. Let's say a star has a uniform brightness coming and luminosity is very constant. How would you measure the distance from that index?
Sorry, how would you
Measure the distance. As you suggested, it's a standard candles. Those are used for measuring stellar distance.
Yes.
So how would you do that?
So, so there is an inverse square law that we have, that luminosity is inversely proportional to the square of the radius, square of the distance from us to the object. So using that law, once you know the intrinsic luminosity of these stars, that is very well known for our analysis. And then you have the period luminosity relationship. Using that, you figure out the apparent magnitude of the star from here, and use the inverse square law to then find the distance to the star.
Inverse square law will give you the flux, okay? But there is a logarithmic relation as far as I know between the magnitudes and the distance. So this is one description, if I am correct.
There, between the I'm not sure.
When you're talking about the parameter fitting, there were about 14 parameters. Is that what you relaxed in the last slide?
Yes.
So these are these physical parameters, you know, you have.
Yes, these are physical.
But the parameters, as many parameters were not shown in the equation that you had.
So in the equation, so all the parameters like the amplitude, the temperature, and the peak brightness also differ with bands. For
They
one
also
star.
had some parameters, I mean, they were kind
So
of
if
governed
you-
by multi-parameters, many
Yes.
parameters.
If you add them up, like you have amplitude in 4 bands, template also in the 4 different bands, and the peak brightness also in the 4 different bands. That's 12. Plus the period and the phase shift and the phase. No, sorry, the period and the phase shift would give you 12. So 14 plus period and the 12 plus the period and the phase shift. That's 14.
What does this phase shift represent?
Right. So the phase shift. Okay. So when we're taking the data, it's in something known as the modern Boolean data. So the phase shift is basically just an offset. It's a constant value for a particular band, for a particular star. It's
Yeah,
just,
for a particular star.
yes, for a star.
That depends on bands also.
No, the phase shift is for a particular star. We're looking at a star. It's just an offset from the actual tape.
So what I get from your work is that this is a new light of environment that was developed. You only tested it for lines. Was this symbolic? Since it's a light curve module, right? Light curve module can be used for various variable stars.
Right.
Not only RR module.
Yes.
Why did you choose to work with only a particular category of RR module?
Because the bigger picture is to find the extent of the dark matter halo surrounding the Milky Way. These stars are the most distant stars known from the galactic center, around 300 kiloparsecs.
So RR are even found in the bulge of the galaxy.
Right,
Not only
but
at the edge of the window, but in
these,
the bulge of the
yes,
galaxy.
but these stars that we have, so these are from the NGDS, the survey. They're studying the Virgo cluster, but the stars that we want are in the foreground of that cluster. So this is why we work with this particular
This
star.
particular
Yes.
set of.
Yes.
Did you actually test your, can your light curve model be tested for CFID or any other?
That is a good question. I think so from what I know, CFID and RRIA differ on the basis of period and on the basis of masses of the stars. So yes, I think this model could also work with CFIDs. But no, we haven't tested that out.
And one last question. Did anybody make metallicity measurements using your tighter model?
That was, yes, that was a part of the project. I don't think I have the. Yes, we did have many diagrams that we made. So I do not know the whole theory behind this, but I do know that they are made to find the metallicity. What we did realize was that after the algorithm was changed, the metallicity, what was thought to be the earlier was like, it was wrong. What we thought the metallicity of the stars was earlier was very wrong, and we found that that also changed after the algorithm was improved.
Because that's a very important test for an algorithm to, when you are making metallicity measurements with the one last. What data did you use? Did you use the Gaia? You know which data?
Photometric data,
Photometric data from
the next generation Google cluster.
engines.
Okay, if I heard you correctly, did you mention that RR layers are not in hydrostatic equilibrium?
Yes.
How did you conclude that?
How did we conclude that it's okay? Firstly, like we know from just looking at variable stars that their intensity changes with time.
C-fields are
Yes.
also variable.
Yes.
Are they in hydrostatic equilibrium?
No. Stars like Cepheid and Ara Lyrae are not in hydrostatic equilibrium. So
All pulsating star, doesn't sun pulsate?
no, the sun doesn't pulsate.
Okay, thank you.
We are at the end of this Meera Memorial Paper Presentation Competition. I would like to invite Debalshi to deliver the vote of thanks.
Thank you everyone. I know it's late. Just like yesterday, I promised I would correct it. If I got corrected, I'm sorry. But thank you everyone for coming all the way to the Ashoka participants. I hope it was an enriching experience. I'd like to thank my council, all the third year members, second year council, whoever is present here. Without them, it wouldn't have been possible. And finally, thank you to the judges. And I request all of you to wait patiently for the results. We'll let you know soon. And before leaving, let us gather all on the ground for a photograph. Thank you.
I want to say something. If everybody is here, I really want to appreciate the amount of effort all of you have put in the kind of work you've done. I am super impressed with each one of you. I mean, I must say, this generation of students does extremely good. And I'm really impressed. This is something I would really want to point out, that the kind of presentations, the kind of work we've seen in last 2 days is commendable. Right? So it's for you all deserve a round.